All right, well, thank you everybody for coming back to this second lecture on tomographic image reconstruction. Again, if you weren't there, the previous lecture, I'm Guillaume Prats. I'll be basically reviewing how tomographic image reconstruction is done for the different type of medical imaging that I covered during this, this class. So to start, just wanted to do a brief recap of the previous lecture, just visually, summarize what we talked about. So we're talking about imaging distribution of radio tracers that are distributing in the body in 3 dimensions. And we're trying to create cross sections of the tracer. So if this is sort of a cross section through the patient with radio tracer distributing, in that space, in 3D, we're looking at a 2D section here just to keep things understandable on the paper. And we do a scan of the patient using either PET scanner or a SPECT scanner. These are tomographic type of imaging. And as we talked about, we collect something called a sinogram, which is a function of theta and r. And sinogram is looks like a superposition of sine waves, as we discussed, and such and such. And in the sinogram, so each, if we look at just each kind of column of the sinogram here, corresponds to a set angle, for example, theta equals 0, and it corresponds to a projection view like this, right? So that would be the theta equals 0 projection view, where we're measuring a projection of the whole tracer distribution in 1D. And so as the gamma rays have been detected, we're kind of recording that and putting it in this sinogram here. And the second thing we talked about was the fact that if this is a 2-dimensional distribution, we can talk about a Fourier transform of that distribution. So this is the Fourier transform, and we can go in the frequency domain. So originally here, this is the spatial domain X and Y, and we can go in the frequency domain, which would be Kx, which is the spatial frequency, Ky, and then in the center we have the low frequency component, the DC term, the 0 frequency, and then it's symmetrical in 2D, the spectrum, and then as we go away from the center, it's the high frequency component. And the key thing we had explained last time is that if we take a Fourier transform of the sinogram here, so a Fourier transform in 1D, so taking a Fourier transform in this direction, so we take each column of the sinogram and take a Fourier transform. So what we're getting basically is the same thing as we're getting here in 2D. So by taking a Fourier transform of the sinogram, each of these row will actually be corresponding to a line in the frequency spectrum of the image. So this black line I showed you here is going to be this line here. And if I show you, for example, I take another line in the sinogram here, so this is maybe theta equal 90 degree. I take a Fourier transform of this, so this is going to correspond to this one here. Okay, and then just to drive the point home, if I have another one, let's say 45 degree right there. So, and I take a Fourier transform here, it will correspond to this one here, I believe. Okay, and so by taking a full sinogram, taking all the angles, we're basically ending up measuring all the information we need in the Fourier domain. And once we have collected all the information in the Fourier domain, it's fairly straightforward to go back to the spatial domain, because essentially we can go back and forth between the frequency domain and the spatial domain using those Fourier transform and inverse Fourier transform. Okay. And actually, so the other thing I wanted to clarify, so we don't actually do use Fourier transform when we do reconstruction. We actually will instead do an operation called back projection. And because of the sort of one of the feature of back projection is that it just keeps adding up the low frequency, so it oversamples the low frequency compared to high frequency. So then we just filter the projections, and then we do filtered back projection, and that will give us the reconstructed image. So from the sinogram, we can go back to an estimate of the tracer distribution using this filtered back projection. So filtered back projection, FBP. So we don't really have to actually manipulate data in the frequency domain. We can do everything in the spatial domain using filter back projection. The filtering that's done can be done in the frequency domain, but it can also be done using convolutions. There's different ways to do it, keeping the data in the spatial domain. But anyway, so this is just a brief review from last time. And then I will move on to sort of the next section of this two lectures, which is iterative reconstruction. And if you remember, I had introduced this mathematical problem last time to kind of give you an idea of the different type of image reconstruction. And that said, how would you solve a mathematical problem like this? And I think one of you had suggested we could do a method using an iterative approach where we try different values of x, and we essentially have a method to get better and better estimates of x until it converged to the solution, right? And so for image reconstruction, it's going to be quite similar. So the general workflow for image reconstruction done in an iterative manner is going to be, so this is the general workflow. So we're going to start with a guess. So here a guess is going to be an image, of course. So we're going to make some sort of guess about the image, okay? So here, in the case of the equation, you could have guessed maybe it's 10, right? And then you could calculate whether 10 plus 15 square root plus square root of 10 is 15 or not. So here, typically for the guess, we will start with either, we'll typically start with a uniform image that's just filled with constant value. It could be ones, for example, it could be zeros. But we'll start with a constant image. So that means we make no sort of prior assumption about the image. We'll just say it's a blank image, and we're going to test it and see if it matches the measured data. So that's the idea, is that we can take this image and then we can estimate the projections. So estimating projections means we're going to take the image and then calculate the sinogram that corresponds to this image. So this here will give us a sinogram, but that's the estimated sinogram. Okay, and again, so sinogram is r theta here, and the image is x, y. So it's kind of a different type of structure. This is not an image, this is a sinogram. And so for my scanner here, we have a PET scanner or a SPECT, or it could be a CT, MRI, it doesn't really matter. But we have a measured sinogram that's here. So the measured sinogram is here. That's been measured by our imaging scanner. And the question is whether those two things are equal or not, or at least are they close to each other, close enough that we can conclude that the image is a correct guess. Of course, on the first trial, the two are going to be different, unless, I guess very unlikely by chance you find the correct answer. And so we're comparing those two, right? And comparing means we're doing some kind of mathematical operation where we either subtracting the two and looking at the difference, or we're taking a ratio, or we're applying some kind of distance metric. And we want to have some kind of idea, how big is the difference between those two images? So some kind of metric that allows us to compare two sinograms. And then we end up with an error term here. So that's the difference between the two images. It could just be it could just be the mathematical difference between the two images. And somehow we'll feed this error term back into the image to improve it, to improve our guess. So if we go back to the simple example here, and if I put it 10, basically I get something that's too small. And so my error term may be, so this thing here minus this thing here. And then if it's negative, then we're going to put a bigger value of x, whereas if it's positive, we'll put a smaller value of x, right? That's how we would update this variable here. And then so here we could do something similar with the images, okay? Okay, so that's the general workflow. Now I just need to introduce a few things about this process, right? The first thing is here, so I said estimate projections, but we need to explain how do we estimate projections? How do we calculate a cytogram from an image? And then the second thing is how do we update the image, right? These are two really crucial things that we need to define. And I would add a third one, which is this comparison here also is kind of crucial. And so I will just briefly walk through this. So the first one I'm going to talk about is how to estimate projection. And we're going to use an operation called forward projection. So forward projection is something that's going to be used for reconstruction. So the idea is if we have a, we're starting with a, this is an image, right? This is my current image estimate. And let's assume it looks like this. And we're trying to estimate the projection of this image onto a sort of a virtual camera, right? So this is actually being done computationally. And so again, we can assume, we have those integration lines going on here. And then, so if this, let's say if I call this R, then we can we want to kind of calculate what's the function going to look like here, right? So this is integrating the radio tracer distribution along those lines. So here this is zeros, and then like here there may be larger values and zero again. And so integrating over those lines, okay? And so that we can calculate S of R theta. So in a way, this is the opposite of reconstruction because we're starting from the image and we're going towards the cyanogram. So I'm going to call this image here f of x, y. And we have y and x, again, are the coordinate system here. Okay. So the way we do that is, so if we assume a discrete image, so this is, if I actually draw this as a discrete array of pixels like this, and then each pixel has different values inside the image. We have different pixel value. So then we have those lines of integration here. So these are we're trying to integrate the image digitally, numerically along those lines of integration. So the way we're going to do that is simply by using a sum formula. So Sj, so this is the cyanogram element number j. So these are, we're going to call these the fi, right? So each pixel has a unique index I, and the value of the pixel is f index I. So Sj is going to be equal to sum of all the pixel fi. So from, we're going to say we have n pixels, okay? So n pixels, but then there's some kind of weighting factor, right? So if we're looking at, this is line number j, for example, the pixel that's out there, quite far out there, does not really, should not really be included in that sum because it's too far away to really contribute counts to that line of integration, right? If there's a radioactive decay here, it's very unlikely that it's going to end up being measured on this line here. Whereas the pixel that's actually being intersected by the line of integration will probably contribute counts to the line. So then there's going to be a higher coefficient. So the idea is we put a coefficient here, A of ij, okay? So A of ij is a big matrix, and the matrix says whether each pixel I contributes to the cyanogram element j, okay? And so what we're saying here is basically that imaging is a linear problem. So it's a linear, actually a linear system. So this whole process of imaging a distribution of radio tracer using a scanner is a linear problem. And so we can write it as a linear combination such as this, okay? And so here I just want to clarify, so pixels are, so it's I equal 1 to n, and then sinogram elements, it's j equal 1 to p, okay? And so because of that, we can write the whole process using a matrix vector multiplication. So I can write it as S equal a matrix A times F, okay? Where this is the sinogram, this is the image, and this here is what we'll call the system matrix. So this big matrix tells me everything about the system that has all the information about the system, the PET system or the SPECT system. So for any pixel in the image, it maps those pixels to all the sinogram element in the image. And so this allows us to, given any image, to calculate the estimated sinogram we would get from that image. So the size of A is n times p. So n is number of pixels, p is number of sinogram elements. And usually we have p greater than n. So typically we acquire more sinogram measurements than we have pixels in our image. So the system is overdetermined, so we have more measurement than unknowns. The matrix is very large, so we should mention that A is very large. Just to give an idea, so n typically could be 10 to the 8, and so n is the number of pixels. P could be even larger. P could be, well, maybe similar. So P is the number of sinogram, but it could be 10 to the 9 in some cases. It really, kind of depends, but it could be very, very large. So, we're ending up with a very large number of elements in this matrix. And so therefore the matrix is, it's not a matrix that you can easily just store sort of, in your computer because it's very large. So typically, well, it can be, a lot of the matrix elements are 0. So, it can be stored. It's not impossible. So it can be either computed and stored. Or it can be sort of computed on the fly. So the idea is, having a mathematical formula for the matrix. And then each time we need to access a row or a column of the matrix, we can just compute that on the fly. Okay, so there's two approaches to handle this very large matrix. And so let's see. What is forward projection? Yeah, so forward projection, going back to forward projection. So forward projection is basically taking an image F and multiplying it by matrix A. So this is the forward projection. So I taking F, multiplying matrix A times F, and that gives the sinogram. So that's what we'll call forward projection. It's basically multiplying by matrix A. And I wanted to just maybe, and since the class has, kind of a diverse pool of students, just actually write the matrix, what it looks like. So when we write this here, this equation, so what we mean is, so we have S here, so this is the vector S. So we'll start with S1, And at the bottom, we have SP. So these are all the sonogram elements. Remember, I showed you a sonogram is a two-dimensional structure, but you can actually take all the elements and put them in a single column like this, right? So this would be, the first X element, maybe the first angle, and then there you have the next angle and the next angle. You put everything in a single row, like line them up into a single row. And then each sonogram element has a number from 1 to P. So S is equal to the matrix, right? So the matrix is this big bulky structure here. At the top, we have A11. There we have AP1. Here we have A1N. And then at the bottom, we have APN. Okay, so this is this big matrix that has all those coefficients in them. Most of them are 0, like I said. Actually, there's no diagonal. I shouldn't be drawing a diagonal because the matrix is not square. So it's a rectangular matrix. And then, so what we're going to look at is the rows and the columns, right? So this is a column of the matrix. And this down there is one of the row of the matrix, right? And then we have, here we would have F. So F is the image. So this would be F1 ... Fn. So this is it. So what does the mean? Like what do the columns of the matrix mean? So basically, if I put a point source as the image, so a point source is an image that has a 1 and then that's zeros everywhere. Okay, this is called a point source because it's a single pixel that's non-zero. So if we set a point source in the sort of field of view of the scanner and we apply the matrix to the point source, then in terms of computing the matrix, what you'll see is, so the matrix vector formula, we will go and then everything will be 0 except for that one column, right? So each time we get to the 1 here, we'll basically use this coefficient, but all the other ones will be zeroed out. And because of that, we end up basically, so we'll end up using all the coefficients that correspond to a single column here, okay? And so this is called the point spread function. Point spread function. So the rows, the columns of the matrix are the point spread function. So each column is a different point spread function for a different location of the point source in the field of view. So that's what it is. And then the rows of the matrix are actually corresponds to the line of integration, right? So if we look at the formula for the matrix, so this is a single line. And so if we're looking at a single sonogram element here, you can see that we're using all those matrix elements in the calculus. So this is the line of integration. So this actually is an image in terms of the number of elements. It has n elements, right, from 1 to n. So this actually is an image. And this is the image that represents this line of integration for this particular sonogram. And if you actually picture the image, you can plot it on the screen and it actually looks like a line. Okay, it's the line of integration. So this is basically the line profile or line of integration. So each row of the matrix is a different line of integration and they give rise to different sonogram element. And each column is a sonogram in itself, right? Because it has P elements and it's the point spread function. It's the result you get if you put a point source in the scanner, you get the sonogram you get. It is a sine wave, right? Because remember we said, if you put a single point source in the field of view of the scanner, you get a sine wave. So if you were to plot this on the screen, what you would see is a sine wave, okay? So these are sonograms, these are images. So this is trying to understand what this matrix is, this big matrix. And that matrix is used for reconstruction. Any question here or? Okay. So now the next operation that's needed for reconstruction is back projection, and we've already talked about back projection a bit, so this should be hopefully a little bit easier to understand. So back projection is as previously explained, but in that case we consider back projection with no filtering. Okay, so back projection takes a sinogram and basically applies the sinogram and converts it into an image through a process of smearing the data through the different projection views. And mathematically, I'm not going to show it here, but so mathematically, back projection is actually a quite simple operation. If we use the matrix, so it's the operation that takes a sinogram S, and it gives us f of b, which is the back projected sinogram, equal A transpose times S. Okay. So in order to back project a sinogram, all we have to do is to transpose the system matrix and then multiply the sinogram by the transpose of the system matrix. Just going back here, so when so the transpose of a matrix is, so transposing the matrix means we'll take this coefficient here and this one here and swap them, and do the same for every coefficient here and here. They basically get swapped, and so the whole matrix is being flipped along its axis, so that if the matrix originally was, so the matrix originally was kind of long and skinny like this, after transpose operation is going to be short and fat. Okay, so this matrix that was kind of taller, now it's going to be shorter and fatter. So the matrix is being flipped on along its diagonal, essentially. I mean, it doesn't have a diagonal, but it's being flipped. Of course, the thing that's, maybe not intuitive is that A transpose is not the same as A inverse. So, if you've taken classes, you may have heard of A inverse, the inverse of a matrix. So A transpose is not the same as A inverse. So the back projection of the sinogram is not the same as inverting the projections, right? And we've seen that if we just apply simple back projection, we don't get back the image that represents the true value of distribution. We get a blurred version of it, right? If you remember, like the simple back projection gave us a blurred version of the image. We had to filter the projection in order to truly get the right answer. So that's this idea here that the transpose is not the same as the inverse. And therefore, because of that, if I apply A transpose to AF, so AF would be like a sinogram. So this is a sinogram. So this is an image F that's been projected. If I apply A transpose to this, we do not get F back. Okay, we get something that's a blurred version of F. Actually, we've seen the blur, right? We've talked about how we get a blurred version of the image. And I also would like to point out that A inverse does not exist. And the reason is that inverse only exists for square matrices, and this is not a square matrix. This is a rectangular matrix, so it doesn't have an exact inverse, right? You could have an approximate inverse, in some sense, but don't have an exact inverse matrix that would kind of cancel out matrix A. Okay, so the reason it's not a square matrix. Okay, so all right, so now I've introduced those two operations, forward projection and back projection, and we can use them for iterative reconstruction, right? So just going back here, remember we had mentioned we're going to talk about three things: how to estimate projection, how to compare projections, and how to update the image. And so basically what's going to happen is that this is going to be our forward projection here, so which is used to generate sonograms that corresponds to a given image. And here we're going to have the back projection, which takes a sonogram and then brings it back into the image domain. And then the last thing we have to talk about is this comparison, how it's actually computed. Okay, so this is, so now we're going to iterative reconstruction. Okay. Okay, so for iterative reconstruction, we have S, which is our measured sonogram. And the goal is, so the goal is to find F, which is an image, such that A of F is more or less equal to S, right? So we want to find the image that when projected using the matrix A gives us the sonogram that was estimated by the sonogram that was measured by the scanner, okay? So this is not an equal sign, just want to point that to the fact that, because again, A does not have an inverse, there may not be an image F that exactly gives us S, right? So there's no exact inverse we could apply. So when I say approximately equal, we're going to try to minimize some distance. So the idea is we're going to try to do, so distance between S and A of F is minimized, or minimum. So distance, you know, so these are two vectors, right? S is a vector, A of F is a vector, they're both sonograms. So think of it as kind of geometrical distance. It could be the Euclidean distance, it could be different ways of comparing two vectors, whether they are the same or not. What's the distance between those two vectors, right? So the question is, you know, what distance to use? And we're gonna briefly talk about two different distances that we can use. So one is called the Euclidean distance. So L2 equal that's kind of the traditional distance you use in space, you know, in 3D or in higher dimensions. And so when you use L2, basically this is called the least square. So we're trying to minimize the least square error. So trying to minimize the distance between AF minus S square. So this is how we represent the distance. So this distance works well if the noise is Gaussian. So if the noise is Gaussian distributed or normal distributed, so the idea is, so this process of measuring distribution of tracer is idealized. There's actually noise being added to the system. So when we have a tracer distribution F, not only is the matrix applied, but there's also some noise that's being added. So if the noise is Gaussian, so if there's Gaussian distributed noise, then doing least square error actually would be the ideal, this would be the ideal way of doing it. Okay, so mathematically we could prove that the solution we get through this process is the best. However, the problem is that the noise in PAD image is actually not Gaussian, it's Poisson, right? So for Poisson noise, we have another type of distance that's more appropriate, which is called the log likelihood. So this is a statistical function, and the likelihood represents the probability of having observed a sonogram S given a image F. So it's probability of observing S given F, okay? And I guess the advantage is that it can model Poisson noise. So Poisson noise, I don't think I have time today to explain it, but the lecture note kind of explain briefly, you know, what it's mean, what Poisson noise is, and why it comes up in PET imaging. It's the key thing you need to know about Poisson noise is that it's first of all, Poisson noise takes only positive values. So it's and the reason is that we're making a PET measurement, we're counting number of radioactive decays. So it's by definition, it has to be a positive number. There's no negative number of radioactive decays. And also it takes integer values, right? So that's another key thing is when a variable is distributed according to Poisson, it only takes integer values. And because we are counting number of radioactive decays, these are integer number. You get 27 decays, but you don't get 32.5, right? You can't really get a fractional radioactive decay. So Poisson noise is really ideal to model data that's coming out of a PET scanner or a SPECT scanner. And actually many different type of measurement processes have Poisson noise in them. Anytime you're counting photons or counting electrical charges, there's going to be Poisson noise. So anyway, so Poisson noise is the type of noise that's really dominant in PET data or SPECT data. And the advantage of this log likelihood distance, which is based on a statistical consideration. So the advantage of that is that we can model Poisson noise, and it will give us an optimal, essentially it will give us an image F that's optimal in terms of the statistical noise. So that's the advantage. And so yeah, so we can model Poisson noise, and what we want to do is maximize the log likelihood. Okay. So now you may ask, you know, how do you maximize? So first of all, what does this log likelihood function looks like? So mathematically, it actually can be written down in a quite simple form. I won't show it here, but there's a short formula that includes F and S. That's the log likelihood function. And then we can maximize it using an iterative approach, right? And the name of the algorithm used to maximize the log likelihood is actually conveniently named the maximum likelihood expectation maximization algorithm. So it's called maximum likelihood expectation maximization. And you know, the easy way to remember this, it's called MLEM. Okay, so that's the name of the algorithm. And it's the algorithm that basically will find the image F that has the highest probability, that's the most probable based on the data S. So S is the data, F is the unknown, right? And it's modeled according to Poisson noise. And so, so this is the algorithm. So I'll just write it down. So first step is initialization. So so if you remember, we said this is the general workflow for reconstruction. The first step is start with a guess. Okay. So the guess here is so we'll start with F0 equal. Basically, it's going to be a vector that's all ones. Okay. So it's just assuming a uniform image to start with. So if you draw it, you know, X, Y, completely uniform. All the pixels and voxels are the same. And then there's going to be iteration. So iteration means we repeat the same procedures several times until we reach some kind of criteria. So the iterations are going to be, so based on a current estimate of the image, we're going to calculate fn plus 1 equal. Actually, I probably need more room. Let me just write it a little bit lower. Fn plus 1 equal. So we're going to start with S. So this is the data. So we have our data, that's coming from the scanner. And then we have our previous image estimate f of n here, okay? So the MLEM algorithm is going to do this operation first. First, we're going to apply matrix A to the current image estimate. And so this is a forward projection. Okay, so this is a forward projection. We're taking the current data, projecting it into as a sinogram. So we're getting an estimated sinogram here. So we're getting an estimated sinogram, and then we're taking a ratio. Okay, so we're taking the measured sinogram S, taking a ratio with the estimated sinogram. So this is actually how we compute the error. Remember I said we were going to compute the error between the sinogram that's measured and the sinogram that's estimated. So it's done by taking a ratio. So it's not taking a difference, it's taking a ratio. And so why is that? That has to do with the MLEM algorithm and maximizing Poisson noise. Okay. So now we have a ratio of 2 sinograms. So picture that this ratio taken, element by element, right? So this is what I mean when I take a ratio. It's the first element of the sinogram divided by the first element of this sinogram. So we have a sinogram that's a ratio of 2 sinograms. So we're going to take this, and now we have to go back into image domain. And so we do that by doing a back projection. So we're taking this sinogram, applying A transpose that gives us a back projection. So now we've taken the error back into the image domain here. And so now that we have the error in the image domain, we have to apply the error, this error correction term, to the previous image. So that's here. We're going to take f of n, that's the previous image, and we're going to multiply it. So here, multiply is again, it's for each pixel. So this is so it's a pixel. So it's a pixel by pixel multiplication. So this is an image. This is an image, and we're just going pixel by pixel and multiplying. So it's pixel by pixel. And the last thing we have to do is there's some kind of normalization factor here, 1 over n. It's just in order for the algorithm to be stable, there's a normalization, and you don't have to worry too much about this. But just know that there's this normalization term. It's actually a constant, so this doesn't change. So it's the same for all the iterations, okay? So that's the algorithm. And so let me just write down maybe more as a process instead of writing as an equation. So the process would be like this. So process is, so first we're going to take F0 and apply a forward projection and get a F0. So this is the forward projection. Then second, we're going to take the data S and divide it by a of F0. So that's taking the ratio, calculating the error term. Then 3, we're going to apply the back projection to this. So this is bringing the error back into the image space by back projection. So this is a back projection operation here. This is just a ratio. Oops, ratio. And then so the last one is, so actually not the last one. Number 4 is to apply this correction to the previous image estimate. So take F0 and then multiply by A transpose S over A F0. And then the last term is divide by divide by n. So that's normalization. So this normalization term, okay? so that's essentially the 5 steps that are done. And then once we've done that, because it's an iterative method, basically the process is repeated for a number of times. And and how many times is it repeated? It depends on the goals of the reconstruction, the level of detail that's aimed for. It depends on the amount of noise. So there's some criteria essentially. So either the algorithm will be run for a set number of iteration or until some criteria is reached. Okay. And so this is kind of, you know, the key reconstruction method for PET and SPECT. The main issue, yeah.
Oh, I just have a quick question. Have you already gone through the description for the back projection process, how to assign counts to pixels based on how much the line is intersecting those voxels? Like side-ons method, that kind of thing, or is that a little kind of extra detail that you?
Yeah, I guess I kind of skipped a little bit over that.
But anyway, just when at a convenient time, you know, I think that was something.
Well, so I mean,
so
I talked about, you know, yeah, I think it's a good point. Here, you know, so we talked about forward projection, which is, you know, so basically following the line and then reading out the pixel value and summing them using a sum formula, right? So when we do back projection, it's the transpose, but in terms of the actual computer work of doing the operation, what's happening is that we're still following the line, but instead of reading the pixels and summing them up, we are writing values into the pixels and adding up. So in the back projection, we would follow line J and then read this pixel and add some amount, some number to that pixel and then write it back there. And then for each pixel that's intersected by the ray, we're basically doing that. And the goal is to, if we have a projection, so this would be the projection here, try to take this projection and smear it across by essentially kind of drawing into the image the values of the projection. So it's, you can think about it like, you know, having a paintbrush and just kind of painting that pattern all across the image. And I'll show examples using MATLAB, and I think hopefully this will become more clear. But basically this pattern here is going to be smeared across the image, and then we'll repeat that for a different angle and add up the values across the image. Yeah, yeah, that's a good point. All right, so so now I wanted to talk about sort of the issue of computation speed, right? And that's, yeah, that's just the last thing here. So fast reconstruction, how do we make this faster? So it turns out that this operation here, forward projection and back projection, are pretty costly in terms of computation. So nowadays, of course, you know, computers are much faster than they were when these things were invented. But still, I think, not long ago, it took, large clusters of computers just to run these operations, because again, those metrics are very large. There are many data points, and it's iterative, the process to be repeated, 100, 200 times. And so they would need for fast reconstruction. And that's when an algorithm called OSEM was invented that basically takes this process but makes it much faster, okay? And so OSEM stands for Ordered Subset Expectation Maximization. So it's a sort of a variant of MLEM. And so the idea behind OSEM is that if we have a sinogram like this, theta r, this is the sine waves, with the EM algorithm, what we would do typically is we would have to, for each iteration, we're using all the data, right? So sinogram has many measurements in it, so it's a very large structure. And then, so for MLEM, each iteration is using all the data. So for OSCM, it's doing things a little bit more smartly. So I don't know if you can see the color on the camera, but yeah, this is supposed to be red. So for OSCM, so let's see, this is our cyanogram. So OSCM is going to do this. So it's so for the first iteration, it's going to use a subset of the data. So it's going to assume the only data, that only angles that are available are those angles, okay, and ignore the other angles. So this would be for iteration number 1. So for the first iteration, it's going to run this whole process that I show here using only a subset of the data. Then for the next iteration, it's going to do the same, but use a slightly different subset of the data. So this would be for the second iteration. Okay. And then for the third one, I think you got the point. For the third one, it's going to use another subset. And the subset can be made so that it's sort of logical and it's easy to program. And at the end, once it reaches, let's say iteration number 15, for example, then after that, it's going to go back to its subset number 1, right? Because once you've used all the data, then you can go back and start with the first subset that you have. And then so for iteration number 16 will actually be done, or sorry, 16 here. So iteration number 17 will be done using the first subset again, right? So there's the idea is that the cyanogram is going to be split into subsets of data. You could have 16 subsets, 8 subsets, 32 subsets. And in the iteration, we're using a subset of the data. So what happens is that those metrics are much smaller now. Each iteration, the matrix is slightly different, but it has much fewer rows, basically. And so that speeds up the process considerably. And now, again, I'll show some examples of that. Yeah. Okay, so actually, I think now may be a good time to do some examples. So just, I think I'm pretty done with the camera, but let's see. So, okay, just give me a second here. I'm going to connecting. Sorry, I think my connection broke here, but okay, I'm going to share my screen. Okay, hopefully you can see my screen right now. If not, just let me know. Okay, so so first of all, I'm going to show some example here. So this first example is showing filter back projection. So we're going to start with the point source. This is a MATLAB code, and happy to share it if through the website if any of you is interested. So I'm loading a point source into the program, and then I'm going to come to the cyanogram. Is working. Sorry, I think it's responding to something. I tried it just before, but I don't know. Let's see. I think I may have to restart it. Just give me a quick second. All right, let's try that again. Okay, there it is now. Okay, so this is the point source. I just put, a single pixel that's non-zero. And what you can appreciate here that when I calculate the cyanogram for this pixel, so I'm basically doing a forward projection here. I get a sinogram function of theta and r, and it's a sine wave, right? So, so basically, as we talked about, so now I can reconstruct the sine wave using filter back projection. So this is first the reconstruction with no filter, so no ramp filter. And this is the output. So this is the initial point source. After a filter back project, all the projection lines, what you can see here is there's a halo around the point source. So first of all, the point source is no longer sharp like it was, and there's this halo around. So that's the blurring I was talking about, is that because of the lack of a filter in the projection, we end up losing some of the high frequencies. And again, that's because the projection operation will basically emphasize low frequencies versus high frequencies. And so we're losing some of the high frequency content by doing this operation, okay? So the solution to that problem, or actually, yeah, let me run the animation first here. Okay, so this is kind of related to Craig mentioned, but this is the actual back projection operation taking place. And you can see that it started with simply smearing the sinogram data across the image, and then it's sort of rotating around and giving us, so this is giving us the full reconstruction after running through that. Actually, let me just, actually I was doing, maybe I'll do it this way here. Doing it again, you can really see the, so it's smearing the projection and adding it up to the previous projection. And then, so this is no filter. Yeah, the first one I ran was with a filter, but this is the one with no filter. Okay, and now you can see the point source with no filter. This is the one with the ramp filter showing up here. I guess, not surprisingly, the image is almost the same as what you had at the beginning. Slightly different because of interpolation, you know, the way the data is handled, that creates maybe a slight halo around it, but essentially it's the same as it's the same that we had input in the algorithm. And then I wanted to show, you know, actually, so what I wanted to show is the effect of noise. So what happened when we have noise? So let's see how we do that. I forgot. I think we just do it here. I'm going to add noise to the data and see what happens. So now, you know, so fewer counts in the sinogram. You can see that the counts are like, actually some of them, we have some of the projections, we have 0 counts here. So this is a very noisy data set. And we'll see if the algorithm can handle that or not, right? So if we do the simple back projection with no filter, you can see, we can sort of see there's a point source, and you can see sort of the noise now is visible in terms of the pattern of the lines that have been back projected. You can see sort of the star-shaped pattern here. And then if we put the filter, so remember what I said, like when you put a filter, it's going to exacerbate the noise. So with the ramp filter, so this is what it looks like. So now it's it gets very noisy, and there's sort of artifacts that show up in the image. So now we, if a point source is maybe not the most realistic example of image for testing a reconstruction algorithm. So I'm gonna load, I'm gonna load a test data set here. So this is supposed to be a brain phantom. So assume that's a brain scan. We can calculate the sinogram for this brain scan. And so what you can appreciate here is the sinogram. So this is essentially a sinogram taken from this whole brain scan. And it has that sine wave pattern to it, right? You can sort of, if you look at it, visualize the superposition of sine wave we talked about in the class. But this is a very noisy sinogram. And so when we reconstruct the sinogram using different methods, we'll see the effect of noise. So first of all, so this is simple back projection, and you can see the image is very blurry. I mean, you can sort of guess that there was a brain image somewhere here, but it's because of the blur and the noise, it's really hard to see clearly what's going on. And now if we apply the ramp filter, if we put the RAM filter here, so now in that case, this is an extremely noisy image. That's very hard to read again. So because of the RAM filter, the high frequency noise has really blown up, and you can see actually a lot of details in the image, but it's mainly due to noise. None of the details are really from the original phantom, right? So the high frequency noise has been amplified by this RAM filter. And so then we mentioned in the class, we could apply low pass filtering during the RAM filter. So for example, the hand filter is an example of that. And so if we reconstruct the data with a hand filter, you can see there's an improvement in the quality of the reconstructed image, right? So it's not great because this is a very noisy data set, but the image at least is, it's easier to appreciate what the image originally was. I think I may have pushed the noise a little bit too high in that example. All right. And maybe I could try again with slightly less noise here. So I'm just going to put 10 times less noise. This is the sinogram corresponding to that. And now if I go in the reconstruction here, sorry. Yeah, so if we do the reconstruction here, so now we actually have, so this is with 10 times less noise. And now, that's a fairly good image that's coming out of the reconstruction. Yes, there is noise, right? Because when we do a measurement, there's always going to be noise. But now it's the signal to noise ratio is much more favorable. Okay, so this is filter back projection. And then now moving on to MLEM. So first, is there any question about filter back projection maybe before I move on? Okay, so MLEM. So MLEM is a similar algorithm, but here we define the number of iteration. And so let's just run it here. Let's see. Okay, so this is a measured sinogram on the left here. This is the image for the first iteration, and as you recall, the image for the first iteration is a guess, and it's the image that's all white, just all ones, right? So we assume first the image is all ones, and this is the estimated sinogram that corresponds to this image on the left. So if I just forward project an image that's all ones, this is the sinogram that we get. If we compare the two, obviously the two sinograms are quite different. So then I'm going to iterate. So now this is the second iteration. So what happened is we took this image and we compared it to the measured sinogram, and then we back projected the error and then corrected the image. And this is, you can see sort of a shadow of the image starts to show up here, okay? So then third iteration like this, fourth. So two things to notice is as we iterate, the sinogram here is starting to look more and more like the sinogram on the left, the measured sinogram. And the image also, the contrast of the image is increasing. So we're starting to see the details more clearly as we iterate. And so, yeah, I think the main effect of iterating here is really the contrast going up. The other thing you may notice is the image is getting sharper and sharper. And the smaller details are becoming more apparent as you iterate, okay? The flip side of that is that as we iterate, basically there may be a little bit more noise that's visible in the image. The image may become more grainy because of noise. So the iterations are running here. So you can see now it's kind of slowing down in terms of updates. So we've already done about 80 iterations, and it's going to run about to 100 iterations, and it's going to stop, okay? All right. Okay, so it's done 100 iteration, and now that's, it's an acceptable image quality for this level of noise. And, it's pretty close to the image we had at the beginning. You could see that it ran pretty fast on my computer. So two things about this. First, this is a 2D, it's kind of a two-dimensional reconstruction. So two-dimensional is much easier to do than three-dimensional, obviously. And then it's a fairly small image. So, normally like the image, number of elements in the image will be higher, there will be more projections and so on. So, so it's not necessarily a realistic data set here. It's more like a data set for demonstration purpose. But nevertheless, so reconstruction can be slow, and MLEM is known to be a very slow algorithm. So there's, OSEM is the faster way of doing the reconstruction. And so I'll show you here. So this is now looking at OSEM, which is using subsets of data. Okay. So this is again the measured sinogram, but in OSEM, we're actually not considering the whole data set. We're only going to consider a very limited number of subsets. So what you see on the right here, these are the subsets. These are the projections that we considered in the current subset. So this is for subset iteration 1. Sub-iteration 1 corresponds to subset number 1. And we're only considering maybe 1/16 of all the data in that example. Okay. And so after applying the iteration to the first subset, the image that comes out is not very clear because of course it has very limited data in it. But you can essentially it's going to look better as more subsets are used. So now the next subset is slightly shifted. So now it's going on the next subset of data and the next subset and so on. So just running through all the subset of data here. Actually, there were 10 subsets. So I went to the background. Okay. All right. And so you can see here, basically it's using different subsets of data for each iteration. And the image that's being generated is very similar to the one we saw with the full MLEM. And because this version of the code uses 10 subsets, it's actually 10 times faster to compute than the previous one. And it essentially converges to the same solution, or at least pretty close. All right. Any question on this or? A bit here. Okay. Okay, so, and the last thing I wanted to show here, I wanted to show some examples of PET images that were reconstructed. Let's see, some example of PET images. Sorry, I just need to find the. Okay. Yeah, just a little bit slow on the computer here, but it's loading. Okay, so just in the last 5 minutes or so, just quickly showing a few examples. So first here, this is an example of a MLEM algorithm. So it's a real clinical data set. I think it's a head and neck tumor. There's a uptake here, and this is just to show basically a common feature of MLEM, which is that as more and more iterations are performed, the noise is going to be amplified. So, so this is kind of interesting that the quality of the images coming out of those iterative methods depends on the number of iteration. And sometimes it actually may not be desirable to run a very large number of iteration because you can see here, so this is sort of the advanced number of iteration. The image becomes very noisy and has that kind of star-shaped pattern. I mean, you can see a lot of noise coming out. And actually an earlier iteration may have been better. And so there's a trade-off really when we run iterative method between getting sharp details to come in focus and then controlling noise, right? And so, depending on the task, depending on the goal of the imaging and the reconstruction, the number of parameters may be different, right? So there's really no answer. What's the optimal number of iteration for a given algorithm? It depends on the data set, and it depends on the tasks that's for which the images are being used. So this is, well, this is just kind of showing again expectation maximization using ordered subsets. So I think we talked about this. Another point I wanted to briefly touch on is that there's other benefit using iterative reconstruction. And one of them is that we can actually incorporate a lot of information in the system matrix. So when we do filter back projection, we assume the image acquisition process is this sort of idealized projections where each, the rays are perfectly thin and they're perfectly straight and so on. But in reality, because the scanners are constructed using detectors, they're not perfect. The detectors have finite sizes, there's physics going on. And because of that, the images will always have some artifacts in them because of the construction of the scanner and the physics. And so one way to address those limitations is to actually incorporate these effects inside the system matrix. And this is an example showing the benefits of using an inaccurate system matrix versus a simplified matrix. And this here, what people did is that they actually took a point source and they used a robot, XYZ robot, to scan the point source inside. So this is the PET scanner here. This bore is where the patient would go. And they're scanning the point source inside the bore of the scanner. And for each position of the point source, they're measuring a sonogram. And if you remember, the system matrix we said was, so the system matrix was, so the system matrix, the rows of the system matrix, sorry, the columns of the system matrix were the point spread function, right? And so we can actually measure the point spread function and fill in the system matrix using a physical measurement process. And so when we do that, the images that come out of the reconstruction will be better. There'll be lower noise, and the details also will come out a little bit sharper. So that's, the advantage of having iterative reconstruction is that a lot of correction can be kind of built into the reconstruction process. So talking about image correction, there's other types of correction. One of them is called attenuation correction. And this is because if a radioactive atom decays that's sort of deep within the tissue, the 2 photons that emerge may get attenuated. They may be absorbed by the tissue themselves, so they may not be detected because of that. Whereas if a radioactive atom is right on the skin, very close to the surface, the 2 photons may be able to emerge without any significant attenuation. And so when no attenuation correction is performed, there's this skin effect where basically the radioactive concentration appears to be higher near the skin, but that's essentially an artifact. It's just due to differences in attenuation between the surface of the patient and then deep inside the patient. And so by doing iterative reconstruction, we can do some type of attenuation correction to account for that. And so typically the CT scan is used for attenuation correction, and it gives this type of images. And so this has been corrected for attenuation. And another type of issue is scatter correction. Same here, so some of the photons are scattered, and by using a correction for that, we can improve the contrast. So contrast between the lesions, so here I guess there are lesions in the liver that become much more apparent when scatter has been corrected. Okay, so I think, let's see. Yeah, this is summary, and I think I will stop here. So we talked about image reconstruction, 2 major methods. Filter back projection, so it's based on the radon transform. I mean, I guess really it's based on this idea of that in the frequency domain, that projections are essentially the same as sampling the frequency domain. And it's using a continuous to continuous system and calculus. And so what are the advantages of filter back projection? Well, the advantage is the model is fairly simple, so it's easier to analyze from a mathematical perspective, right? We can understand resolution, we can understand noise and so on. It's linear, and also it's fast to compute. So that's a big advantage, is very fast, and it's easy to invert. Whereas, so MLEM, so it's based on the system matrix. And so here we're using linear algebra, and we're using also noise models based on statistics. The advantage is it's potentially very accurate, so it gives the best image quality. But because it's a very large matrix, I guess the model is harder to invert and requires iterative methods that can be quite slow. Okay, so I think I will stop here.